Okay, let's unpack this. There's this sort of fundamental divide in astrophysics. It's not something people talk about a lot, but it really dictates what a researcher spends their life on.
It does. On one side, you have the mechanics.
The engineers of the universe, exactly. These are the folks who are just obsessed with the machine of it all. The Big Bang, how galaxies spin, the fundamental forces. They want the blueprint.
But then there's the other type.
And I think this is the group that gets most people excited in the first place. These are the people who can't shake that little question whispering in their ear.
Are we alone?
Right, the existential detectives. And today, we are diving deep into that second group. Specifically, we're exploring the work of Professor David Kipping at Columbia University and his lab, which is dedicated to finding what he calls cool worlds.
And just to be clear right at the top, when he says cool, he's not talking about, popular. He means temperature.
The temperate zone.
The Goldilocks zone, yeah. But he's looking for planets that are further out from their stars. Places where you could have liquid water, where you could have moons, wings, where you could have biology.
But that's not what we've been looking for, is it? For decades, our methods have been biased.
Massively biased. We've been finding hot Jupiters, gas giants orbiting their stars in just a few days. Not because they're common, but because our tools are just really, really good at spotting them.
So this whole deep dive, which is based on a fantastic conversation between David Kipping and Lex Fridman, is about correcting that bias. It's about the detective work needed to find these cooler, quieter worlds.
It is. We're going to get into the hunt for the very first exomoon and some truly radical ideas for future telescopes, like using the entire Earth as a lens.
We'll definitely get to aliens and simulation theory too, because Kipping has a pretty unique take. But let's start with the hunt itself. Why is finding an Earth so incredibly hard? Kipping has this great analogy.
Oh, the party analogy. It's perfect. It's the best way to explain the transit method.
Just set the scene for us.
Okay, imagine you're at a party. It's crowded and you've lost your glasses, so everything is just a blur. You can't make out any faces.
Right, just shapes and colors.
Exactly. But you can see the bright lights on the wall. And if someone walks in front of one of those lights, you see the light dip. It gets a tiny bit dimmer.
So you didn't see the person, but you saw their shadow.
You saw the occlusion. That is exactly how we find planets. We stare at a star, a light bulb, and we wait for it to blink.
Sounds simple enough on paper.
Conceptually, yeah. In practice, it's a geometric nightmare. For you to even see that blink, the planet has to pass directly between us and its star.
The alignment has to be perfect.
Perfect. For a hot Jupiter orbiting super close, the odds of that alignment are actually pretty good for astronomy, about 1%.
Which I guess in this field is a luxury.
It's a shooting gallery. But now, take that planet and push it out to where Earth is. The orbital path is so much bigger, so the angle for that alignment gets way, way tighter. Your probability drops to, what, 0.5%? Maybe less?
So for every 400 sun-like stars you stare at, maybe only one have an Earth lined up just right.
And that's not even the worst part. The worst part is time. A hot Jupiter zips around its star in a few days. If you see a blink on Monday, you just wait till Thursday to see it again. You can confirm it in a week.
But an Earth takes a year.
A full year. And to be sure a signal is real, to prove it's not just some glitch in your telescope, you need to see it at least 3 times. That's the gold standard.
So you have to stare at that one star without blinking for 3 years.
Which brings us to what Kipping calls the great tragedy of the Kepler mission. Kepler was the space telescope built to do exactly this.
And it was brilliant. It found thousands of planets.
Thousands. But its reaction wheels, the little gyroscopes that kept it pointing steady, they started to fail after about 4 years.
Oh, no. 4 years.
Yeah.
That's just enough time to maybe get your 3 or 4 transits for an Earth-like world.
It was heartbreaking. They were right on the edge. They saw hints, maybe 1 dip, maybe 2. But the telescope broke before they could get that crucial third confirmation. So if you look at the official catalog from Kepler, the number of confirmed Earth twins around sun-like stars is 0.
0. After all that work, that's staggering.
We found planets around smaller, dimmer stars, sure, but a true Earth analog. We missed them by a whisker. And the signal itself, Kipping puts it in perspective. He says detecting an Earth crossing the sun is like trying to spot a firefly flying in front of a stadium floodlight.
84 parts per million. That's the number. The light dips by 0.008%.
It's excruciating. And yet, Kipping's team is trying to do something even harder. They're not just looking for the planet, they're looking for its moons.
The hunt for exomoons. And my first reaction to this is just, Why? I mean, isn't finding the planet hard enough?
It is, but the moon might be what makes the planet special. Look at us. Our moon is huge compared to the Earth. Its gravity is what stabilizes our tilt.
So it gives us stable seasons.
Exactly. Without it, Earth's axis would wobble all over the place over millions of years. The climate would be chaos. And then you have tides. A lot of theories about the origin of life start in tidal pools, that cycle of wet and dry.
So if you find a gas giant in the habitable zone,
Yeah.
you'd normally just ignore it.
Right, you can't live on Jupiter, but you could live on one of its moons. All of a sudden, that gas giant becomes a piece of prime real estate. You might be doubling the number of habitable places in the galaxy.
Okay, so they go back to the Kepler data looking for these tiny, tiny signals, and they find a candidate, Kepler 1625b.
This is probably the most famous and most controversial case out there. 1625b is a Jupiter-sized planet, but it's on a 287-day orbit, so it's a cool giant.
And when they look at its transit, the light curve, it just looked weird.
It was messy. The dip wasn't a clean U-shape. It had these little extra dimmings on the edges like shoulders, but the real smoking gun was the timing. The planet showed up 20 minutes early.
Which is called TTV, right? Transit timing variation.
Exactly. A lone planet is like a perfect clock. Tick-tock. But if it arrives early, it means something else is pulling on it gravitationally. When they ran the numbers, the only thing that could explain both the weird shape and the early arrival was a moon.
Ooh. Not just any moon.
No. The data suggested this moon was the size of Neptune.
A Neptune-sized moon orbiting a Jupiter-sized planet. That just sounds wrong. We have nothing like that.
It breaks a lot of our models for how planetary systems form. And this is where the story becomes a really good lesson in science. Kipping's team didn't celebrate.
They tried to kill it.
He says they threw the kitchen sink at their own hypothesis. They spent years trying to prove it was a mistake. Was it a spot on the star? A data glitch.
But the moon signal just wouldn't go away.
It held up, but, and this is a huge but, in frontier science, other teams have looked at the data and found weaker signals or interpreted it differently. It's still in this limbo. It's evidence for a moon, not a discovery of a moon.
It just shows how hard this is. You're at the absolute limit of what the technology can do.
Right.
Which brings us to the next challenge. Okay, let's say you find the cool planet. You even find its moon. Now you want to know if there's life. The first thing everyone says is, look for oxygen.
And Kipping basically says, warning, that is a trap.
The oxygen trap, because here on Earth, oxygen means photosynthesis. It means life.
But you can get a planet swimming in oxygen with absolutely no life at all. This is a huge problem for planets around red dwarf stars, which are the most common stars out there.
Like the TRAPPIST-Swift system.
Exactly. Red dwarfs are. Well, they have a violent youth. They blast their planets with intense ultraviolet radiation. So if you have a planet with oceans, that UV light hits the water vapor in the atmosphere.
When it cracks the water molecules apart.
It's called photolysis. H2O splits into hydrogen and oxygen. Hydrogen is super light, so it just floats off into space. The oxygen is heavier, so it sticks around.
And over 1 billion years, you build up a thick oxygen atmosphere on a planet that's now a barren, waterless desert.
A total false positive. A dried out husk that looks, from a distance, like a paradise. And then there's the other problem, what he calls the moon deception.
This one is so clever. It's a problem of resolution, right?
It is. Remember, for these distant worlds, even with the James Webb Space Telescope, a whole solar system might just be a single pixel of light. One dot. Now imagine in that pixel you have a planet with water clouds, and right next to it, a moon like Titan with a thick methane atmosphere.
Okay, so 2 separate dead worlds.
But your telescope can't tell them apart. It just mushes their light together. So the spectrum you get shows water and oxygen from the planet and methane from the moon all mixed up.
And oxygen plus methane is a classic biosignature. They shouldn't exist together unless something is constantly replenishing them.
You'd think you'd found life. You'd hold a press conference, you'd be on the cover of every magazine, and you'd be completely wrong. You were just fooled by 2 dead rocks sitting too close together.
It's terrifying. We even saw a version of this with the Phosphine on Venus story, right? One team thought they found a sign of life. Another team said it was probably just sulfur dioxide.
Finding life isn't going to be one aha moment. It's going to be decades of arguing over squiggly lines on a graph.
So if our current telescopes are hitting these fundamental limits, Kipping has this radical idea. Don't build a bigger telescope on the ground. Use the ground as the telescope.
The terrascope. Yeah, this is one of those ideas that sounds like total sci-fi, but the physics is 100% sound.
So how on earth does that work?
It's not about gravity, which is what you usually hear. Earth isn't big enough for gravitational lensing. This is about our atmosphere. It's about refraction. As starlight grazes the very edge of Earth's atmosphere, the atmosphere acts like a lens and bends the light.
Like light passing through a glass of water.
Precisely. It bends the light by about 1 degree. And if you trace all those bent rays of light, they all come together at a focal point.
And where is this focal point? On the other side of the planet.
Well, way on the other side. It's out past the moon, near the Lagrange points. But if you could park a detector there, looking back, the entire Earth becomes your lens, a lens 12,000 kilometers wide.
They're turning the whole planet into a telescope aperture.
And it would amplify the starlight by tens of thousands of times. With that kind of power, you wouldn't just see a dot. Kipping thinks you could actually resolve continents on an exoplanet, see clouds, see seasons change.
That's unbelievable. So what's the catch? Why aren't we building this tomorrow?
The lens is dirty. The atmosphere is a mess, right? It's got clouds, turbulence, storms. It's like trying to see through a constantly shifting, foggy piece of glass.
So the image would be a total blur.
Without correction, yes. You'd need incredibly advanced adaptive optics on your detector to cancel out all that atmospheric noise in real time. But Kipping's point is that nature has already built the expensive part. We just have to be clever enough to build the eyepiece.
It's a hack of physics. And he seems to love these kinds of hacks, which I think leads us to techno-signatures, looking for things that aren't just life, but engineering.
Right. He published this amazing paper on something called the halo drive. It's a way to power a starship using a pair of black holes.
Using black holes as an engine.
As a sort of refueling station. Imagine 2 black holes orbiting each other. If you shoot a beam of light or particles around one of them in just the right way, gravity acts like a slingshot.
It whips it back around at you.
But it comes back with more energy than you sent it with. It steals a tiny bit of momentum from the black hole's orbit. A ship could use this to accelerate to, incredible speeds without carrying any fuel.
So we should be looking for spaceships hanging around binary black holes.
Or maybe we should be looking much, much closer to home. He has this beautiful idea about how an advanced civilization would communicate. Not with radio. Radio is temporary.
It fades out. The civilization dies. The signal stops.
Exactly. If you want to communicate across deep time, millions of years, you build a monument. You carve your message in stone. But you don't put it on Earth, because Earth has erosion, tectonics. It erases its own history.
You put it on the moon.
The moon is geologically dead. A time capsule buried there could last for billions of years. He suggests that maybe the best place to look for an alien message isn't a distant star, but our own backyard. We should be scanning the moon for artifacts.
It's straight out of 2001, A Space Odyssey.
It is, but it's completely logical. It's the ultimate message in a bottle.
I do want to touch on one last thing before we wrap up. The simulation hypothesis. People like Elon Musk have said it's almost certain we're in a simulation. Kipping disagrees.
He argues the probability is actually less than 50-50, and his reasoning comes down to computing power.
The cost of running a universe.
Right. Think of it like a set of Russian dolls. You have base reality. They build a computer to run Sim 1, but Sim 1 can never be as complex as base reality because the computer itself is part of base reality. You always lose some fidelity.
And if the people in Sim 1 build their own simulation, Sim 2, it's even lower resolution.
Exactly. You go down the chain, and each reality gets simpler, more pixelated. Eventually, you hit a level that's so low fidelity it can't run complex physics, let alone consciousness. Kipping calls this the sewer of reality.
The sewer of reality. I love that.
So his argument is that most possible realities in this whole stack are these sewer levels that can't simulate anything else. Since our universe appears to have consistent, complex laws, and we seem to be on a path to eventually building simulations ourselves, we're probably not in the sewer.
We're probably near the top of the stack.
Or we're base reality itself. It's a surprisingly optimistic argument that, yeah, we're probably real.
I have to say, I find that weirdly comforting.
Me too.
So when you pull back from all this, from blurry transits and Neptune-sized moons to using the Earth as a lens, what's the big picture here?
I think Kipping's work is part of a larger shift. For centuries, astronomy was about mechanics, about predicting things. Now it's about looking for cool worlds. We're looking for ourselves out there.
It's that second type of astrophysicist, the existential detective, finally getting their moment.
And Kipping's whole philosophy is that even if we never find anything, the search itself is what matters. He calls science a ride.
The universe is a ride.
Yeah, there might not be some grand cosmic purpose to it all, but getting to observe it, to try and understand it, to spot that one little firefly in front of a giant floodlight, That's what makes the ride worthwhile.
It really changes how you look at the sky. I mean, tonight, if you look up at the moon, don't just see a rock.
See it as a potential library, a place where a message could be sitting untouched for a billion years, just waiting for someone to get clever enough to find it.
Or maybe waiting for us to leave a message of our own. That's a powerful thought to end on. Thanks for taking us through this.
Anytime.
And for everyone listening, keep looking up. We'll see you on the next deep dive.